All right, I'm going to begin now. Share my screen. Okay, we're going to revisit reactions of alkenes. I'm going to do some review and then we'll look at some new material. Okay, got a few more people joining. Okay. All right, the most common reactions of alkenes are addition to the double bond, which transforms the pi bond into two sigma bonds. And this is often exothermic. All right, again, these are three broad classes of reactions. Okay, we've looked at elimination and substitution, and in this chapter we're looking primarily at addition. The alkene group consists of a sigma bond and a pi bond. The pi bond is electron rich, so it will attack electrophiles, species that are electron deficient. Okay, so this is the pattern for electrophilic addition. Okay, we'll see some variations of this, but in general, the double bond picks up an electrophile. Okay, one of these electron pairs is used to form this bond, and so this carbon is missing a bond, and so it carries a plus charge. Okay, in the second step, the nucleophile attacks, and we get our addition product. This is the overview of reactions we'll be looking at in this chapter. Okay, they don't all follow this pattern, but we'll look at some of them that do at first. Okay, so here is addition of a hydrogen halide, HCl, HBr, or HI. First step is the double bond picks up a proton. The proton is the electron deficient part. Okay, that gives us a carbocation, and then the halide ion, bromide in this case, attacks the positively charged carbon, forms a new covalent bond. Okay, if the alkene is unsymmetric, this reaction is regioselective. That is, it prefers a particular positional isomer. And Markovnikov's rule provides us with a guide. Okay, the rich get richer when it comes to hydrogen, so the other side gets the plus charge. And so here we have an unsymmetric alkene. And so the bromide will end up on the more substituted carbon, the tertiary carbon. The tertiary carbocation is formed faster and it's more stable than a secondary. Okay, and this shows the reaction energy diagram. Okay, the tertiary carbocation you can see is formed faster and it is lower in energy, more stable. The second step has about the same activation energy, but it's much faster to get to the I'm sorry, this is primary versus secondary. I said secondary versus tertiary. But in this case, the secondary is more stable than the primary. Okay, here's one example. Okay, when we add HBr to this double bond, okay, it goes in this orientation and not in this orientation. Okay, because this will go through the tertiary carbocation. Okay, just a few more examples. Okay, rich get richer. Okay, so this side has one hydrogen, this side has none. And so this side gets the hydrogen. This is our product. For this alkene, this side has one hydrogen, this side has none. And so we get this product. And another example here with HI. Right, I goes to the position with the fewest hydrogens. Okay, we'll have two exceptions to Markovnikov's rule, and we call those anti-Markovnikov. It's in quotation marks because actually the more stable intermediate is formed. That's the extended Markovnikov's rule. Okay, this says in the presence of peroxides. Okay, peroxides, remember, are ROOR. HBr adds in the anti-Markovnikov orientation. Okay, this particular reaction only works with HBr. Okay, only HBr will give the reverse orientation. And this was actually discovered by accident. Okay, some chemists saw some unusual results, unexpected results, and it turned out that their reaction mixture was contaminated with peroxides. Okay, it does not work with HCl or HI. So if you have HCl and peroxides, the peroxides won't make any difference. You still get the Markovnikov product, same way with HI. Okay, so first you have an initiation. The bond between the two oxygens is very weak. It breaks symmetrically. Okay, this is endothermic, but it doesn't take much energy to break it. And then the alkoxy radical removes an H from HBr. And you use a single barbed arrow. Right, this pair of electrons splits up. So that gives us ROH, and it gives us a bromine free radical. Okay, so one electron went this way, one electron paired up with this unpaired electron. Okay, that bromine free radical then attacks a double bond. The pi bond splits up. Okay, so one electron pairs up with the bromine to form this covalent bond, and the other electron is left behind on the carbon. Well, bromine will add to the less substituted side because that gives the more stable intermediate, namely the secondary free radical in this case, as opposed to the primary. Okay, and then we have several other things that can happen. This is another propagation step, for example. The free radical can remove a hydrogen from HBr, give the product. We could also have a termination step, and several other things could happen. But this gives the anti-Markovnikov product. Right, the intermediate tertiary free radical in this case forms faster because it is more stable. Okay, so the question here is convert 1-methyl cyclohexanol to 1-bromo 2-methyl cyclohexane. All right, we can start with 1-methyl cyclohexanol, do a dehydration, okay, like we did in lab a couple weeks ago. This is the Zytep product, the most substituted alkene. And then we would do an anti-Markovnikov reaction with HBr and peroxides, and that would give us the desired compound. Okay, let's look at hydration of alkenes next. Okay, this is actually the same mechanism as dehydration, but it's in reverse order. And instead of removing H and OH from adjacent carbon atoms, we're adding H and OH to a double bond. Right, this follows Markovnikov's rule. H goes to the side that already has the most hydrogens. OH goes to the other side. Okay, and remember when we did the dehydration, we used concentrated sulfuric or phosphoric acid. Here, you would use a dilute solution of phosphoric or sulfuric. Okay, we want to shift it toward product by having lots of water here. Okay, this does require an acid catalyst. Okay, that's why it's dilute sulfuric or phosphoric. Okay, so in acid solution, strong acid will form hydronium ion, and the water is not acidic enough, but hydronium ion can be protonated, and H will go to the side that's richer in hydrogen, and the other side gets a plus charge. Okay, the second step is water attacks, and the third step is deprotonation to form an alcohol. And that also regenerates the hydronium ion. Okay, so just like with addition of hydrogen halides, this forms a more stable carbocation and follows Markovnikov's rule. I'm going to go ahead and show this again. Just like with HBr and HI and HCl, hydration can produce rearrangements because it does go through a carbocation. Okay, so for example, starting with 3,3-dimethylbutanene. Okay, this is the actual product we get. Okay, so initially, okay, carbon number 1 picks up an H. That puts a carbocation on carbon number 2, which is secondary. And then because of a methyl shift, that produces a tertiary carbocation. All right, then water attacks, we get deprotonation, and this is the major product. Oxymercuration, demercuration is a way of adding H and OH while avoiding rearrangements or polymerization. Okay, mercury acetate dissociates to form Hg acetate plus. That is the electrophile. The double bond attacks. And when it does so, it forms a 3-membered ring called a mercurinium ion. And this reaction does follow Markovnikov's rule. Okay, so here's mercury 2-acetate dissociating. Right, the double bond attacks the Hg plus acetate. This mercurinium ion is it's a 3-membered ring. And because of this ring, okay, that prevents hydride or alkyl shifts. Okay, they don't occur because of that. Okay, water will attack the more substituted side. And then another water removes this extra hydrogen. Okay, so we get this organomercurial alcohol. Right, and then sodium borohydride replaces the mercury with a hydrogen. Okay, so the advantage to this is it prevents rearrangement. Okay, here's one specific example. This is the same alkene that we used just a minute ago. Okay, back here, and we saw the methyl shift take place. Okay, with the oxymercuration demercuration, we form this 3-membered ring which prevents the methyl shift. Okay, notice here water attacks the more substituted side. Okay, because the more substituted side is better able to stabilize this partial positive charge. Right, we have addition of water, removal of a hydrogen, we get this Markovnikov product. NaBH4 replaces the mercury with an H. Okay, this is the same mechanism, except instead of water, we're using some alcohol as our solvent. Okay, so R is methyl or ethyl or propyl or some alkyl group. And follows the same mechanism, except our final product will be an ether rather than an alcohol. Okay, it's carried out the same way. All right, hydroboration. All right, this is, yes. Okay, Markovnikov. Okay, Markovnikov's rule describes the regioselectivity or the preference of one positional isomer for another. And if you think about, okay, when it comes to hydrogen, the rich get richer. Okay, so this side has 2 hydrogens, this side has 1. So rich get richer, and we'll get the more stable secondary carbocation. So we'll get this product and not this one. Okay, so this is the only other anti-Markovnikov reaction besides HBr and peroxides. This is hydroboration of alkenes. Okay, this uses diborane, B2H6, or a more convenient form is BH3THF. Okay, here, the electron deficient atom is not a hydrogen, it's a boron. Okay, boron actually is less electronegative than hydrogen, and so the hydrogens won't be partially positive, they'll be partially negative. And then boron only has 6 valence electrons, so it's a good electron pair acceptor. Okay, so BH2 adds to one side, H adds to the other, and then with oxidation using hydrogen peroxide and sodium hydroxide, we get an alcohol with the anti-Markovnikov orientation. Okay, so Herbert Brown at Purdue University received the Nobel Prize in 1979 for his work on borane chemistry. Okay, so diborane reacts with THF, which is an ether, to form this complex. Okay, this is much more convenient to handle. Diborane is a gas, and gases are fairly difficult to measure out. Okay, if you want a certain quantity in moles. Also, diborane spontaneously ignites when it comes in contact with oxygen. This is much more convenient because you can buy solutions of borane THF of a certain molarity. Okay, molarity is already on the bottle, so if you need so many moles, you calculate how many milliliters you need, and then take what you need. Okay, so the more stable transition state would put hydrogen on the more substituted carbon. Okay, it goes through this square transition state. And then the oxidation step replaces the boron with an OH. Okay, this is the reverse of hydration. In hydration, we would have H and OH on opposite carbons. Okay, the stoichiometry is one borane to 3 alkenes. Okay, so before the oxidation, you actually end up with a trialkyl borane. Okay, so 3 alkenes will attack the borane. Hydroboration is also stereoselective. That is, we get a particular stereoisomer. And stereoisomer that we get is the one in which H and OH are added to the same side. Okay, so BH2 and H are added to the same side. They're added cis or syn to each other. And the alcohol and the hydrogen are also syn to each other. Okay, that is, they're eclipsed. They're on the same side of the ring. Okay, usually you can't tell this unless you have a ring. If you have an open chain compound, you wouldn't be able to necessarily see the stereochemistry. Okay, this is what the hydrogen peroxide does. Okay, OH removes the hydrogen. We get the hydroperoxide ion. The hydroperoxide ion attacks the trialkyl borane. We have a R migration, which forms a borate ester. And then this happens 2 more times. We get a trialkyl borate ester. And then hydroxide attacks the borate ester, kicks out the OR minus. This happens 2 more times. And we end up with the 3 alcohols. Okay, this is similar to a problem we had earlier. Okay, how would you convert 1-methylcyclopentanol into 2-methylcyclopentanol? Okay, so here is 1-methylcyclopentanol. We could do a dehydration. This is the Zytip product, the most substituted alkene. Okay, very similar to what you did in lab a couple weeks ago. And okay, and then once we get this, we can do hydroboration. Okay, so here the alcohol ends up on position number 2. Okay, this is further evidence of the syn addition of H and OH. Okay, if we start with this deuterated norbornene, this bicyclic compound, the H and OH end up on the, this is called the exophase. Okay, underneath is called the endo. Okay, notice the 2 deuteriums are at the endo position. Okay, so both H and OH are added from above. This is a racemic mixture. Okay, you have a chiral center here where you actually have 2 chiral centers. This is a chiral center because hydrogen and deuterium are different. Okay, next let's look at addition of halogens. Okay, this is a reaction you'll be doing in lab this week. X2 is chlorine or bromine, or sometimes iodine. Okay, iodine is a little more difficult to add. It usually requires heat. This is not regioselective, but it is stereoselective. Okay, we get anti-addition of the 2 halogens. Okay, and here's why. Okay, we go through this bromonium ion, this 3-membered ring. Okay, so when the alkene attacks bromine, it forms this bromonium ion, or a chloronium ion if we're using chlorine. And then the halide ion, the X minus, attacks from the backside. Okay, so we form a bond here, we break a bond here. It's like an SN2. Okay, nothing happens with this bond, that's still there. Okay, but this bond broke. And because of that, the 2 halogens will be anti to each other. Okay, if the alkene is cyclic, okay, which it will be in your lab on Thursday, okay, we'll form this 3-membered bromonium ion. Bromine attacks, and we'll get the trans dibromo product. Okay, so this is stereoselective. We get the trans, not the cis and trans, not the cis. We get the enantiomer as well. Okay, we would get the enantiomer if bromide attacked the other side, and this bromine was up and this one was down. We can observe this type of stereospecificity in other alkenes, such as cis and trans 2-butene. Okay, if we add bromine to cis-but-2-ene, okay, we'll get 2 enantiomers. Okay, we'll get a racemic mixture plus minus 2,3-dibromobutane. If we start with the trans, okay, we'll actually get the meso. Okay, bromine has a dark red-brown color, and this is a quick test for the presence of an alkene. Okay, when bromine adds to a double bond, it does so quickly, and usually the alkene is colorless, and the dibromoalkane is also colorless. And so what you'll see is a disappearance of the red-brown color, okay, which is shown on the left. Okay, if there's no double bonds present, then of course the color won't disappear, which is shown on the right. Okay, let's look at halohydrin formation. Okay, a halohydrin is where we have a halogen and an alcohol on adjacent carbons. Okay, this is a Markovnikov addition. The halide will attach to the less substituted carbon. Okay, it turns out it's also stereoselective. Okay, so it starts out just like bromination or chlorination. We form the halonium ion. Okay, water attacks from the backside of the more substituted position. Then another water attacks and removes its protons. We get our halohydrin. Okay, it's regioselective. It forms the Markovnikov orientation. Okay, which means the halogen is on the less substituted position and the alcohol is on the more substituted. And it's also stereoselective in that the halogen and the alcohol are anti. Okay, so if we start out with cyclopentene, okay, we will get trans 2-bromocyclopentanol. Okay, so the alcohol and the bromine are trans to each other, plus the enantiomer. Okay, so why doesn't the bromide Br- attack? Okay, if you try to make a solution of bromine in water, okay, it doesn't dissolve very well. And it is difficult to make even a 1% solution. And so you have a few bromide ions, but you have a lot of water molecules. Okay, and the large excess of water molecules will overwhelm any minor contribution from bromide ions. So water is your nucleophile, just because you have so many more water molecules. Okay, so here's an unsymmetric, we started with an unsymmetric alkene. So we form the chloronium ion, and then water will attack the more substituted side. And then we'll have deprotonation, and we'll get the halohydrin. Okay, and this is, that's similar to what we're seeing here. Okay, we go through the bromonium ion, the 3-membered ring. Water attacks the more substituted side. Okay, that opens up this ring. And since water has to attack from the back, okay, the water, or I guess it's the front in this case, the alcohol and the bromine will be trans to each other. And then we'll have the two enantiomers. Okay, while when cyclohexene is treated with bromine and saturated aqueous sodium chloride, a mixture of trans 2-bromocyclohexanol and trans 1-bromo-2-chlorocyclohexane results. Okay, in this case, it's not just water. We're using saturated sodium chloride solution. So in this case, we have a high concentration of chloride. And so we'll get the alcohol, but we'll also get the bromochloro product. And in both cases, we get the anti-stereochemistry. Oops. All right, now we're going to turn our attention to a different mechanism. This does not involve ions. This is one that takes place at the surface of a metal catalyst. Right, so here we have hydrogen gas, and this reaction has an extremely high activation energy, but if we add a catalyst, it can take place readily at room temperature, just a few atmospheres of pressure. Okay, this is often something we can do in the laboratory on the bench top if we have thick-walled glass containers. Okay, so butene adds hydrogen to form butane. Okay, this is called catalytic hydrogenation. Okay, it only takes place if a catalyst is used. It only takes place at a measurable rate if a catalyst is used. Okay, the syn stereochemistry is favored. Okay, so we start out with this deuterium-labeled cyclohexene, and the two hydrogens are added cis to each other on the same face. Okay, this is something called Wilkinson's catalyst. It uses rhodium. I think the primary advantage of Wilkinson's catalyst is it's soluble, so it's a homogeneous catalyst. Okay, the finely divided metals are heterogeneous catalysts. So they, excuse me, just a minute, I'm going to get a drink of water. All right, so here is the heterogeneous catalysis with a finely divided metal such as platinum. It's a solid catalyst. The platinum absorbs the hydrogen, it breaks the bond between the two hydrogens, forms two metal to hydrogen bonds, you can see here. It also binds the alkene, and it adds the two hydrogens one at a time. Okay, so we mostly get the hydrogens added cis. Okay, we may get a little bit of trans. Okay, if this happens to roll over before we add the other hydrogen, but mostly we'll get the syn addition. Okay, this is an example of a chiral catalyst. Okay, this is its structure here. And because of that, we can start with this alkene, and we hydrogenate it stereoselectively, and that gives the S isomer. Okay, Okay, we don't want the racemic mixture because only the S isomer of DOPA is useful in treating Parkinson's disease. Okay, the other enantiomer is actually toxic. Okay, that was one of the examples from the article that I showed you, L-DOPA or S minus DOPA. Okay, next we'll look at addition of carbines. Okay, this is a carbene. It's an unusual species. It lacks an octet. It has no charge, and it is both electrophilic and nucleophilic. So it accepts a pair of electrons to an empty p orbital, and then it donates a pair of electrons and forms this three-membered ring. Okay, this is cyclopropanation. Okay, there are three methods of cyclopropanation. One is to use diazomethane. There's the Simmons-Smith reaction, and then there's alpha elimination of a haloform. All right, here is diazomethane. In the presence of heat or ultraviolet light, it decomposes to form nitrogen gas and the methylene carbene. All right, the disadvantage, there's actually two disadvantages. One is that diazomethane is extremely toxic and explosive. And the carbene can also insert into CH bonds to give you unwanted side products. Okay, so this was a much safer alternative that was developed at DuPont by two chemists named Simmons and Smith. And this is actually a much better way of preparing cyclopropanes than using diazomethane. Okay, if we combine diiodomethane with this zinc copper alloy, okay, we get the Simmons-Smith reagent. Okay, it is a carbenoid. It's like a carbene, but it's not really a carbene. Okay, if we look at the polarity of this bond, okay, iodine is more electronegative than carbon. Okay, so carbon on this side will have a partial positive charge. Okay, without knowing the electronegativity of zinc, metals in general are low electronegativity. Okay, so this is going to be just the opposite. Okay, so here, this will be partial negative, partial positive. Okay, so on one side, carbon has a partial positive charge. On the other side, it has a partial negative charge. Okay, so it can accept a pair of electrons from this side and donates a pair of electrons from that side. Okay, we have about 5 minutes remaining, so this is the alpha elimination reaction. Trihalomethanes are called haloforms. And so here we have bromoform, as it's commonly known, or tribromomethane. It reacts with hydroxide, to form this anion. Okay, the hydroxide pulls off this hydrogen. And then we have what's called a spontaneous alpha elimination, where we have heterolysis, this bromide just leaves, and that gives us a dibromocarbene. Right, the dibromocarbene, again, can accept a pair of electrons, and then it donates a pair of electrons to form a cyclopropane ring. Okay, this reaction is stereospecific. Okay, so the dichlorocarbene adds to one side of the alkene, so the benzene rings, the phenyl groups are trans in the starting material. They're also trans in the product. Okay, so stereochemistry is preserved. Okay, here's a cis alkene. If we use bromoform, okay, we form our cyclopropane ring here. Our ethyl groups are still cis in the product. So the cyclopropanes will retain the cis or trans stereochemistry of the original alkene. Okay, again, to summarize, here's a Simmons-Smith and alpha elimination. Alpha elimination, of course, gives the dihalogenated cyclopropane. Right, epoxidation, this is another lab we're going to be doing this semester. This uses a peroxy acid. Okay, this is like a carboxylic acid, except that we have an extra oxygen, which is color-coded here in green. Okay, and then we get the epoxide or oxirane. That's a three-membered ring with an ether group. And then we get a regular carboxylic acid as the byproduct. Okay, we know experimentally that it is this oxygen, the one closest to the H, that adds. And the way they were able to prove that was to use isotope labeling. Okay, they added oxygen 18. Okay, most oxygen is oxygen 16, but they had a isotope label oxygen 18. Okay, if they put the oxygen 18 label here, all of the labeled oxygen ended up in the oxirane. Okay, if they put it on the other position, all of the labeled oxygen ended up in the carboxylic acid. So they were able to prove that it's this oxygen that was added. Okay. The most common peroxy acid is one that's called MCPBA, metachloroperoxybenzoic acid. And I'll draw that structure. Here's benzoic acid. Here's peroxybenzoic acid. And then metachloro or 3-chloro peroxybenzoic acid, what we call MCPBA. That's the structure. Okay, I'll show you the mechanism, but then next time we'll go through it in more detail. Okay, it goes through a cyclic transition state that looks like this. Like the cyclopropanation, both the carbon-oxygen bonds are added to the same side, so any stereochemistry in the alkene is preserved in the product. Okay, so you start out with a cis alkene, you end up with a cis product. If you start out with a trans alkene, you'll end up with a trans product. Okay, so I'm gonna look at this in more detail next time, and we'll stop there.